The Advances in Data Science seminar series. So it's my pleasure today to have Markus Heinonen visit from Aalto University in Finland. So Markus is an Academy Research Fellow, and I've been following Markus's work for a long time because he's been working on Gaussian processes, which is a technique close to my heart, and he's also been working on biological and biomedical applications of that in the past. So we've sort of, I guess we've cited each other quite a bit, and we know each other's work. So I sort of feel familiar with Markus's previous work on Gaussian processes, but I'm less familiar with the work he's going to talk about today, which sounds really exciting. So Markus is going to talk about the links between differential equations and deep learning and Gaussian processes a bit as well. I think neural networks and Gaussian processes. So we're going to hear about the links between all these exciting things. If during the talk you think of a question, then just put it in the chat and we'll ask questions at the end. You can either put them in the chat or at the end, you can just chip in and talk. But for now, over to Markus, and I'm looking forward to this. Thank you.
Okay, thank you. Thank you for the great introduction, and also thanks a lot for the invitation. It's really great to be able to speak here. Okay, so I'm Markus Heinonen. So I'm working at Aalto University, which is in Finland in the Greater Helsinki region, and I'm also affiliated with the FKI, which is the Finnish Center of AI, which is sort of like a similar network of excellence like Alan Turing Institute in the UK. And so I'm going to now talk for roughly 45 minutes on our work on modeling differential equations with both Gaussian processes and neural networks. And I'm also going to show some of our works on how they're going to connect with deep learning and actually making things like classification by using dynamical systems. Okay. So the motivation for this talk comes partly from classical dynamical systems. So we can look at some simple first principle systems like a motion of a pendulum. And this is like a classical physics thing where we know the governing equations of a pendulum, and we can actually describe them ourselves and write the equations down. And there's no need to do any kind of learning. However, when we go to more complex things like motion capture, where we have some agent who is moving and we are observing the movement over time, this is obviously being governed by physics. But now the governing equations are rather complex. We could have 100-dimensional sensor data coming from this object. There is also things like external forces. The agent could have its own will. It might turn left, might turn right. So this is a very complex thing. And this is already something where we cannot derive the equations by hand. And then we could look into things like video, where we could have 1 million pixels over lots of frames. And now obviously this video is following some kind of dynamical system. However, this dynamical system is very messy, it's complex, and learning it definitely needs deep learning. Then sort of going away from this kind of classical sort of like time series data and fitting time series, we could also look into other connections. For example, in optimal transport, we are transporting one distribution into another distribution, and one could also think of this kind of transport as a flow or as a dynamical system. And finally, to me, actually, the most interesting thing is, can we sort of execute classification as a dynamical system? So conventionally, one would say, okay, this makes no sense. So if we classify these 3 points into 3 classes, one would just do find some kind of mapping function, some kind of discriminant. However, we have models, for example, decision trees, where the decision of which label a point belongs to is made iteratively. And one could model a decision tree as a stochastic process. And then taking this idea sort of further, one could actually say that, okay, we could make a decision as some kind of decision particle moving under some system. Okay, but before we go into these quite fanciful ideas, let's start from the beginning. So our works on dynamical systems started with ODEs. So ODEs are dynamical systems where we are following a state vector as a function of time. So the state vector might as well be parameterized by some parameters theta, by the initial position x0, by some external influences u, But here we are just going to simplify and say we have a parameter, we have a state vector x as a function of time. And in ODEs, the evolution of this state vector over time is governed by the time differential. So we have dx, dt, which we denote with this dot notation. So dot x means what is the differential over time of this state x. And this is now a function f. So this function f is now the prime interest that we want to learn from some observed trajectories or time series data. And this f is now a vector field. So it's a mapping from the d dimensions into the differential of those d dimensions. So it's still a d-dimensional system. And we can see on the right, this gray arrow thingy is basically the vector field. So at any point, we also always have an update direction. And in an ODE, we would then solve the state forward in time by starting from some initial state, and then we go until time t by following this time integral in equation 3, where we are just constantly asking the system, okay, where are we now? What is the next update direction? And then going in infinitesimal steps towards that. And here in equation 3, it's important to note that the xt on the left and the x tau on the right are the same object, just at different time points. And now then in practice, we would then solve this using, for example, Euler method, which discretizes over time. So this is now an approximation. And then we also have more advanced methods like the Runge-Gutta, which is a fourth order, sort of like a nonlinear numerical solver. And here, this system is now fully deterministic. We also assume there's no control, and we also assume there's no time variance here. Okay, and here are a few classical examples of ODEs. So we have Lotka-Volterra and Van der Pol. Both are classical two-dimensional systems where we have two state dimensions, x1 and x2, which are following certain parametric differential equations at the bottom. So we have this kind of 2D plane of dynamics, where we have the vector field, and the red shows a single trajectory, which in this case loops. And then this trajectory can be then decomposed into these two dimensions at the bottom. And for example, the Lotka-Volterra now is quite a common model for this kind of predator-prey dynamics of like having foxes and chickens or something like that. And now, because I'm a machine learning person, so for me, talking about ODEs, I want to learn ODEs. So now we could define the hierarchy of ODE learning problems. So we could start from the first principle models where we can simply define the mechanistic equations by ourselves, but there is then nothing to learn. So then the simplest problem that we could consider is the parameter optimization problem, where we assume that the differential function f is known. So we know the structure, maybe we have some equations, but it has certain coefficients that are unknown. So for example, maybe friction is unknown or masses of particles and so on. And especially in statistics, this has been studied a lot, especially using these kind of gradient matching techniques. And then what we are most interested in is the system identification case, where the underlying system is completely unknown. We simply have some trajectories and we need to learn the whole thing. And now this sounds like a machine learning to me. So now we just would apply here some machine learning kind of black box systems that can then reproduce these trajectories. And this is something that started maybe around 6-7 years ago, where these kind of conventional approaches have been applied, Gaussian processes, splines, kernel functions, and so on. And then 2 years ago, Chen et al. From Professor David Duvenau's group in University of Toronto made a big paper about learning the differential operator as a neural network. And they won the best paper award in NIPS 2018 and have almost like 1,000 citations already on this paper. So these are now very, very trendy topics to study. Okay, but let's look at the unknown system identification problem now in more detail. So we're interested in learning the unknown differential function f from noisy observations y coming from the true state xt corrupted by some noise. And now we observe these observations at certain time points. So in the middle, we see the real data. And on the right, we see the system that generated this data. And now we would like to learn this right-hand side guy so that this matches the data. So in this project, our sort of toolbox was Gaussian processes. So Gaussian processes are a family of Bayesian kernel methods. where the main idea of Gaussian processes is that we are basically applying a constraint that the Gaussian process function covariances between 2 points have to obey the kernel similarity of those 2 points. So what this means is that if we have 2 points that are very close to each other, most likely then the function value also should be quite close to each other. And then this is something that induces usually distributions of quite smooth functions. And here we see 3 examples. So the conventional illustration would be this 1D Gaussian processes. We can obviously also do this for 2D inputs in the middle when we get some kind of surfaces. And then in our case, we are interested in vector fields, which are in this example, it would be from 2D to 2D. And this can be seen simply as a multitask or a vector valid Gaussian process, where we have 2 of these surfaces. And on the right, we see a good example of a relatively smooth vector field, which could be generated by a Gaussian process as well. Okay, so now this is actually what we do. So we place a Gaussian process prior on the differential function f, where we also define a kernel function, which is now technically this is an operator value kernel, but in practice we just diagonalize it. The kernel is a Gaussian kernel, and by placing this Gaussian process prior on the differential function means that a priori we assume that the differential is 0 if we see no data, and its covariance now follows this kernel. And a Gaussian process naturally defines that for any collection of locations in this state space, their corresponding differential functions, these kind of arrows pointing from those places, follow a Gaussian likelihood. So we can evaluate how likely is a certain combination of arrows. Okay, so now we employ a sparse Gaussian process construction, where we are basically populating the state space with a bunch of inducing location sets and associated differentials, which are these arrows from those points. And the idea is that these arrows should match this function definition. And now, since these are now the parameters of the system, and we can now use the Gaussian process mean function conditional, which is basically just kernel regression, to interpolate any arrow between these arrows. So now here we have visualized it, these gray swirls is the vector field underneath, and this vector field is actually just lots of different arrows, but I have visualized in this kind of stream plot way. And now next we can just integrate the system forward using numerical solvers. So we start from the red circle, and then we go with this blue similar trajectory. And now obviously our problem here is that if we now observe some data along this state space, we want that blue curve to match the data. And then we have basically found the vector field you're interested in. And I want to highlight how sort of expressive these vector field parameterization can be. So here we have just a visualization where we only change a single inducing vector, this red arrow. We are changing this where this red arrow is pointing, and the underlying interpolated vector field is also changing, as you can see from the gray stream plot. And also, consequently, also the blue trajectory solutions also change quite drastically. So we can see that the quite small changes in the vector field can cause dramatic changes in the trajectories. So this is a highly nonlinear and highly non-convex learning problem. So this requires us to have very efficient gradient computation to solve this problem, and also in practice also something like MCMC, because we don't want to simply cover a single mode of the posterior. So now how the posterior looks, here is just a sort of a high-level view of the posterior. So we are interested in the posterior in this case of the inducing arrows U at location Z, given the data, which we then use the Bayes rule to transform this in the likelihood and prior. So in this case, the prior is the vector field prior, which is a Gaussian process. So this is the Gaussian prior on the inducing arrows U. And then the likelihood here is the difficult part. So in the likelihood, we have a product over the data points, which are yi's, at time Ti. And then the mean of the Gaussian likelihood function is always the simulated response, where we start from x0 and we integrate forward our own parameterized vector field f. And now the problem is that we have this really nasty temporal integral inside the likelihood. So computing the regular gradient simply doesn't work in this case. So to account for this problem, we have to turn into continuous time gradients, which are effectively the continuous limit of discrete backpropagation, where the gradient of this system actually becomes an ODE itself, or dynamical system, which we run backwards in time. So we start from the endpoint and we run the gradients backward in time, sort of to accumulate all the information of how should we change the system. And here we see these adjoint equations at the bottom, which actually were already derived in 80s by several people, and then now lately popularized by this Chen et al. Paper. And here this gradient of the posterior with respect to, for example, the parameters u is now a backward integral from time t to time 0, where we follow these adjoint parameters lambda, and we multiply them by the gradient of the partial derivative of the system with respect to the inputs and the parameters. I'm not going any deeper here. I just want to highlight this sort of change of gradient convention we have to follow. And then some results on this. So we published this on ICML 2 years ago on this paper, Learning Unknown ODEs with GPs. And here we see 3 examples of these kind of classic toy cases where we have van der Pol, Fichu, Nagumo, and Lotka-Volterra. And here the gray region shows the data region. This is training data, basically one cycle of data from these cyclical systems. And then we learn the system, and then we predict forward to the future. And our prediction is showed with the green and blue regions, and the black is the true. So it seems that we can surprisingly accurately actually now reproduce these dynamics from just one cycle of dynamical data. So this system seems to work quite well. However, it's not perfect. So if we look more closely into the systems, so these are the vector fields of these 3 systems that we studied. And here, I think the gray arrows are probably the correct ones, and the black arrows are our estimations, or vice versa. I now don't recall. It seems that our vector field is quite accurate around the observed data. But as we go away from the data, the estimation of vector field gets quite a lot more erroneous, which is quite natural, because obviously we cannot estimate things that we have no data from. So estimating the vector field is always somewhat of a local problem. So finding the global dynamics is likely impossible. Okay, and then next I would like to go to then stochastic system. But is there any questions at this point before going to stochastic systems? Okay, so if there's no questions, so next we want to study stochastic systems. So the previously the ODEs we studied were completely deterministic. So you start from somewhere, you follow the vector field or the differential, and you always end up in one place. And this is perfectly fine for many applications. But on the other hand, in many cases, you also do have stochastic perturbations on the trajectory. And to account for these, you then have to move into stochastic differential equations, or SDEs. And SDEs are basically ODEs that you augment with a stochastic component. I mean, underneath, the math is quite complex here. So I'm simplifying the picture. But here, basically, we have this kind of deterministic drift vector field, which was similar as before. It's still the gray arrows in this figure. But we also add a Brownian motion or a Wiener process, the DW. And we can also modify its diffusion matrix, which kind of colors the variance of this process. And on the right, we see what happens. So we start always from a fixed point, and we are trying to follow this deterministic vector field, but we are constantly being pushed or perturbed in different directions, in random directions, which then means that the state distribution at some future time is actually a distribution instead of single point. So starting from one blue point, we actually can arrive at a distribution of black points. And this is now quite an interesting model, and this can now model quite complex dynamics. And now, how do we then learn these things? Well, we propose that we would just place two different GPs. We have one GP for the drift, one GP for the diffusion magnitude, which in this case was just a small sigma instead of the capital sigma, because handling these kind of matrix valued things is rather more complex. And here I would just like to highlight the effect of the diffusion here. So if we still have this SDE system, and we now have this sigma, which is the magnitude of these perturbations, these Wienerian perturbations. If we have very small amount of these perturbations, we almost have an ODE system. But as we increase them, we get more and more chaotic system that eventually would basically break down and would not even follow the overall trend. And the interesting case that we studied in our paper was what would happen if we would have a sort of like a hotspot of varying diffusion. So we would have on this left corner, we would have a place where we have lots of diffusion, sort of lots of chaos, and then outside it's relatively deterministic. And could we identify if we have data coming from this kind of system? And now I have just a single example from this paper. We did also other experiments. So this was published in MLSP, which is the Machine Learning Signal Processing Conference. So here we simulated a true SDE system at the top left, where we had a true drift as the gray stream plot, and then we had the diffusion magnitude as these blue circles. At the bottom center, we have data from this system, as well as from in the bottom right. And then based on this data, we then estimated what kind of vector field systems we could generate these kind of things, and then we arrive at the estimate at the bottom left, where we have now associated also this kind of color for each inducing vector that defines the diffusion. So we can reuse these inducing vectors for both the drift and diffusion. And then this top part shows simulated trajectories from this kind of system. So this is quite a complex plot, so I'm not going to spend more time on this. Okay, so one problem in this kind of SDE modeling is that we were placing in two different, completely separate Gaussian processes, one for the drift and one for the diffusion. And we started to think that could we actually combine these two into one? Like, it feels funny that we have two completely different models sort of handling effectively like the same system. So then in the next work that was published in AI Stuff last year, we proposed these kind of differential Gaussian process flows, where we made an assumption that what if we simply say that the differential of the state, so the dx dt itself follows a Gaussian process with a certain mean function mu and a kernel function sigma. And now here, the kernel function doesn't need to be just the prior kernel. It can be any positive semi-definite kernel. So it could also be what one would call a posterior kernel, or just any conditional kernel. And the mean function also doesn't need to be zero. It can be very informative. So in this paper, we actually show that if you make this assumption that the differential of your state is a Gaussian process, then it actually corresponds up to certain scaling factors to an SDE system where the drift equals exactly the kernel mean, the Gaussian process mean, and the square root of the diffusion matrix equals the kernel of the Gaussian process. And then these two terms have these rather pleasing simple forms, at least for Gaussian process people. So what this now really means? So this basically means that if we have at the bottom this visualization, we have at the right, we see a vector field. It's these lines and arrows. And then we also have this color, which is the magnitude of the diffusion. And then at the bottom left, we see an example 2D data, which we have colored just for visualization purposes. They are not labels. And then it means that at every time point, when we move this data forward in time, we are always asking this Gaussian process that which direction do we now move? And the mean is always the mu, and then we are sampling somewhere from u plus sigma multiplied by a Gaussian random variable. So we are kind of moving in this, like we have this kind of drift that says, okay, we should go in this direction, and then we are kind of moving somewhere around it and doing these kind of perturbations. And now we interpreted these things as basically a continuous time limit of deep GP. So one could say that a single layer of a Gaussian process is doing like one step forward in this system, and a deep GP is then multiple steps. So you could say that actually deep GP could be defined from this viewpoint as well. However, there is one crucial difference here, is that in deep Gaussian processes, there is a known pathology that if you apply arbitrary data through several layers of Gaussian processes, you kind of tend to get these kind of slivers of mass. So it seems that the mass is being concentrated and the rank of the system seems to be collapsing. And this has been analyzed in several papers, and there are various ways to sort of counter this pathology. But in our system, if we sort of interpret this differential flow or this kind of SDE system as a deep GP, it doesn't collapse because we have this Wiener process that always perturbs points in relatively chaotic manner. So things can never collapse. Okay. So then the way we actually applied this system was to apply it for supervised learning. So what happens here is that we use the Gaussian process-induced SDE to input warp our data points. And now we are talking just as the classical classification regression settings, things like UCI benchmarks. So we just have some vector value data which have a single output that we want to predict. So what we do is that we define the data points as the initial state of our dynamical system. We apply this SDE flow, which now moves each input around following this vector field system. And then we apply a standard stationary Gaussian kernel Gaussian process on the endpoints, which is the function G. And the idea here is that when we optimize this in end-to-end fashion, because this final classifier regressor G is a stationary function, then it's most optimal if we process the data in a way that any non-stationaries are removed from the data. And this way, the system can fit very flexible data sets. So here we see a univariate example of what's going on. So we can first look at the top part of this figure, where we have a univariate regression function, or just the function, and it has these two jumps at the left, and then it's otherwise relatively smooth. So we are first applying input warping to this data. So because the input is the x-axis, it means that when we warp the input, it can only move left or right. So it seems that it's most optimal to move these points so that at these jump positions, we are moving the data points away from each other. And then when we have moved these data points away from each other using this SDE flow, which also has some uncertainties, we can then just apply a standard Gaussian process at the bottom, sort of representation of the data. And in this system, we never have to sort of go from bottom to up. So we can just always just take the data top, we can go down, process in these new states, and then classify, regress, and we are done. So it seems that this is a very flexible system that could be applied for many kind of problems. And one thing we also studied was that what happens if we make this sort of input warping flow for a longer time. So our hypothesis was that then it has more time and more capacity to remove, for example, non-stationarities, and it seems to work. So when we apply the flow for a longer time, the test error just keeps going down, while the competing methods like the classical sparse GP or the deep GP, 2 layers, cannot really compete. And here in this case, for example, we did 50 temporal increments forward in time. So one could interpret this as a 50 deep Gaussian process. However, the key thing here is that this is an additive model. So each GP, each increment is always adding something to the previous state, while in a Gaussian process or deep Gaussian process, it's a transition function which maps one state to the next state. So it could move in a more erratic way. Okay, is there any questions so far? Okay, so then next in this sort of line of research, we started to think, how can we work with higher dimensional systems? Because Gaussian processes don't really work in high dimensions very well. So we wanted to work with, for example, image data or video data. And what we proposed was a neural ODE, which we apply in the latent space, and where the latent space is generated by a variational autoencoder. So now variational autoencoder is a Bayesian autoencoder, where we have one module that can encode complex object down into a latent vector representation, into latent code, and we have a decoder that can reconstruct the original object. And we of course want the reconstruction error to be very small. So in this case, what we do is that our data is this kind of sequences of images, which now represent this kind of balls in some kind of box where the balls are bouncing. And here we are encoding these frames down in latent space. We are defining a neural ODE in the latent space. It drives this state forward in time, and then we are decoding back to make extrapolation or forecasting, basically to have like simulated dynamics or simulated video. And here the key thing is that the system does not know that there are balls. I mean, the system has no idea what's in these images. I mean, it simply fed a bunch of images, and it needs to learn to reproduce these sequences of images. So it has no idea that there are 3 balls. It has no idea what the location of balls are. It has no idea of the momentum of the system, and so on. And in this case, we also introduced second order ODEs, which basically means that we have position and a momentum of the state, which actually helps learn the system and regularize the system. This is something we published last year in NIPS. And here I just want to highlight few results, because these are pretty cool things. So this was the sort of the bouncing ball example. We have the sequence of balls that are following certain dynamics, and our ODE to VAE model can now simulate and reproduce these until roughly 15 to 20 frames, and afterwards it will start to break down. And we also learned how to rotate numbers. So here the data was bunch of MNIST digits at different rotations in a sparse way, and we learned how to then rotate these numbers, which is somewhat of an academic exercise perhaps. But then we also applied this to motion capture, in which case our data is basically vectors of these different joint coordinates, which we encode into a latent space. We learn an ODE in the latent space that can move this guy forward, and then by decoding we always get a future time state of this stick figure. And here the blue represents the uncertainty we get since we use Bayesian neural networks in this case. So again, it seems to quite well match the true movement, which is the red stick figure. Okay, and then a final example of our line of research then represents going even deeper into partial differential equations. So far we only looked at ODEs or SDEs. So in both cases, we have a single particle that follows its own trajectory. So it's just following its own sort of, okay, it asks the vector field which way should we go, and then it goes there. In a partial differential equation, the direction a single particle goes depends on its neighboring particles, because the time derivative of the system depends on the spatial derivative of the system. So basically neighboring points. And here, this is something that has been actually done already quite a lot. What we proposed was to make this fully continuous time without sort of depending on any particle discretization over time or space, so that we can apply this kind of flexible triangulation and then apply graph convolution neural networks on top of this. And these models tend to be really good at reproducing things like heat equation and things like that. So we see an example here where the data and the prediction almost perfectly match each other. Okay, but I'm not going to go any deeper in this. Okay, so these 4 papers roughly, or 4 or 5 papers now represent our works on learning differential equations from temporal data. And next, I would like to highlight, with just a few minutes, I would like to highlight a few deep learning connections of these things. So I don't see these things as simply models for time series data. I see them as something more fundamental to machine learning. So the first connection is something that was not made by us. So this is by Chen et al. In David Duvenau's group. So neural networks can be seen as mapping a layer representation to the next layer representation through some function f, which represents the layer transformation. And residual networks are a specific type of neural networks where the layers are additive. So we're always adding to the previous layer state something about the current or previous layer. And it was shown in this paper that the continuous limit of ResNets actually becomes neural ODEs. So what this means is that the layer index is not a discrete anymore, but instead it's a continuous variable. So instead of having 1, 2, 3, 4, 5 layers, we just have 5 time units that we can integrate forward at that sort of infinitesimal steps. And this is basically input warping. There's nothing magical here. We are basically just input warping the input signal to go in some place. Instead of doing discrete jumps, we are doing continuous jumps. And obviously this requires some kind of final link function to be mapped into the outputs. And in practice, you would basically define this kind of thing for like a single layer could be replaced by one OD net. Then you do maybe down sampling or up sampling, and then you proceed. Okay. So then one could go forward by also doing ODs for random variables. So here I'm not going to describe the equation here, but normalizing flows are methods where we can take a random variable which has some density, and we can actually let that also evolve under some discrete or continuous flow. For example, on the right, we see a Gaussian random variable, and we can have this kind of vector field that pushes the mass in different places. And this way we can generate rather complex densities from very simple base densities. So this is basically a way to generate more complex random variables. And this is obviously useful in things like density estimation, when we are estimating px, or in variation inference, where we can try to enhance the Gaussian mean field approximation into something more complex. Okay, and then my final sort of proper slide of this presentation is sort of trying to bring together different views of machine learning and differential equations. So I kind of feel that machine learning means that we map from input space X to output space Y. And in deep learning, we map an input space X into successive feature spaces, F1 to FL, and then we map to the output space. And then on the other hand, in differential equations, we map the input space X to itself through the differential operator. And then what I would coin differential learning is something where we map the input space X to itself, and then eventually to the outputs. And there's a beautiful paper by Ohadi and Yu from actually last year on kernel flows. So this was published in Journal of Computational Physics. So these are physics people who kind of postulated this kind of idea that, okay, let's say we have to do the very classic double spiral classification, classify the red points from the blue points. So in one, we see a very complex discriminator. But now if we would have a dynamical system that would warp these blue and red points in a sensible way, we could actually straighten up these lines and make the discriminant become trivial. So we can actually shift the workload from learning a very complex discriminator into learning a complex transformation of the data, and then afterwards, not really having to classify at all, or the classifier becoming basically trivial. So I think this is a really cool idea. because machine learning, I guess, like 95% of machine learning is trying to find classifiers or regressors that are usually more and more complex as we invent new things. But from this point of view, we could also see that, okay, could we actually modify the data to match our assumptions of the system and do machine learning in this way instead? So maybe some new insight might be revealed from this viewpoint. And this is something that has only been emerging for, like in the last 2 or 3 years. So this is a very new viewpoint and only a few papers on this. Okay, so I would like to then conclude with the summary slide. So in this talk, I showed a bunch of works by ourselves on learning differential equation systems or time series models with neural networks and Gaussian processes, and then discussed a bit on this kind of like what I would like to call grandiosely as a new paradigm of differential learning. Some other people might call it by different name, where we have a continuous time information processing system instead of a discrete time. And the open questions are kind of the conventional. So how do we handle uncertainty? How do we solve the numerics efficiently? How do we learn geometries or manifolds or informative structures? So all of these are mostly open questions still in these domains. Okay, thank you very much. Any questions?
Thank you, Markus. That was fascinating, great overview of the field, as well as talking about your work. I thought it was really nice. If there's any questions, people can just shout out, or you can type questions in the chat. But while people are thinking, there was a lot to process there. I've got a question. So it's really interesting to think about this new paradigm of differential learning. I was wondering, what does learning theory look like in this paradigm? So in particular, I was wondering what functions are learnable, and is there restrictions on the sort of topology of data? Because you were talking about warping, and some of your examples looked a bit like unwinding things and you know, changing data until it's kind of in a simple form to learn. But I was wondering if there are examples where that doesn't work, or is it like neural networks? Is there some sort of universal approximation result where, you know, if you have enough complexity, you can definitely learn a function?
Yeah, that's a great question. So I can only speculate here, but I mean, I would now recall like the basics of learning theory, things like Vapnik, Chervonenkis dimensions, which basically say that in which ways we can shatter the data, basically like how many like different regions it consists of. And also we have Rademacher complexity, which basically measures like how can we basically model this kind of chessboard data, which is like structured in a nasty way, but basically just noise. And I think if we look at these kind of transformations, the key thing in differential equations is that they are continuous. And so they are actually not like, you cannot jump. You can only make small, so you can only basically stretch the space. You cannot make like a point jump in a completely different place. So I would actually assume that these behave much nicer than like neural networks that can basically do anything. They can, for example, reorder the points or do crazy stuff. So maybe there could be some connections. Yeah, I believe some connections. The very classical learning theory could be interesting here. For example, in this ODEs paper, they actually related this problem to min-max games, where we kind of have the two classes as two adversarial players who are trying to fool each other. And then the other one is trying to move its points in a way that is confusing for the other one, and then see like what kind of equilibriums we get in the Nash sense. So there's very, very interesting things to study here.
Of course, learning theory is hard enough for standard neural networks. Introducing a new paradigm makes it even harder. Anyone got any questions here in the chat? I think you've blown them away with the with new concepts. I'll maybe take another one then. So the warping, I guess I can understand in terms of the idea of ODEs and deterministic kind of differential equations. If you have a stochastic, if you have an SDE, can that also be used as a warping function? Is that useful? And in that case, do you kind of end up with a distribution on the other axis that you have to deal with?
Yeah, I guess it means that we have uncertain warping, and the uncertainty is of a specific kind, where the uncertainty is in the warping in a very sort of indirectly in the warping function itself instead of just sort of outside. So yeah,
sort of decon. Could that be like having a GPLVM type mapping function or something? Or
yeah, it's similar. It's similar, but I guess in a GPLVM you just have a single mapping from the latent to the data space. In this case, you have this kind of iterative or recurrent mapping, and this can of course accumulate more complex uncertainty. So we can have non-Gaussian uncertainty.
Well, what I'm thinking about is deep GPs, because you mentioned the problems with deep GPs, and somehow the propagation of error through the deep GPs somehow isn't working properly often or something. And I was just wondering if propagating these as SDs might be a good way of propagating complex noise distributions. But I don't know. I had to think about it.
I think, I mean, basically it's a machinery, so we could use it for that. But the main problem is, how do we then define the target uncertainty? How does the system know how much uncertainty and what kind of uncertainty it should try to learn? And this has been quite challenging for us. It's been quite difficult to sort of define like learning targets or loss functions, or sort of like what kind of uncertainty actually we want. Because conventionally we would just look at something like a Bayesian predictive posterior, which usually gets high values when your prediction is very highly peaked at the data points. But this is also something we don't want because it tends to overfit. So balancing sort of, and then the question of what is the prior even meaning if we place a prior on the warping instead of the parameters directly, because then this warping prior kind of then also propagates into some other kind of like more complex prior, I guess.
Okay.
So yeah.
Great. Okay, any questions from anyone? I think people need to go away and read the papers. There's a lot of content.
Can I ask maybe a naive question? Thanks a lot, Markus. It was a really interesting talk. So I work in atmospheric sciences, and you know we're concerned with you know, maybe ODEs with 16,000, 20,000 components, and you know it's a real bottleneck from a modeling perspective, and you know, shunting that into climate models from a regional to a global framework still relies on manual interpretation of the complexity you need to carry that information. And I'm wondering what your thoughts are on the scalability of these type of approaches to systems with that level of variables.
Well, yeah, I mean,